Could we have our next expert in the chair, please? Welcome to the show. Could we have your name, please?
I'm Chris Budd.
Okay, Chris, could we see your theory, please? Thank you very much. Your theory is that there is nothing random about chaos. Okay, what are your qualifications, please?
Well, I'm quite a scary person because I'm a mathematician.
You're a mathematician, okay, and your theory, there is nothing random about chaos. Could you explain that to us, please?
Well, some things in our lives are very predictable. For example, my watch. I know exactly what my watch is going to do in an hour's time. Other things are really random, like my dog. You know, when I let my dog loose in the park, it goes all over the place and you've got no idea where it's going to go. But there are important things in nature which really look random, but are actually governed by quite well-defined scientific laws.
Right, and these laws are what are known as chaos theory. That's, broadly speaking, what it's known as.
Well, chaos theory describes things in nature like clouds, for example, which look random, but the theory behind them is actually quite simple.
The butterfly effect is part of this, isn't it?
Well, there was a theory which came out in the 1960s by a guy called Ed Lorenz, and he was trying to explain the weather. And of course the weather's quite difficult to understand. It changes a lot. And his theory was that if you took a butterfly and it flapped its wings in, say, Venezuela, then the small effect of the flapping of the wings of the butterfly could kind of grow and grow and grow and eventually end up being a hurricane in Bristol, for example.
Right. I can't help noticing you got a machine, Chris. What's that for?
Well, this is to demonstrate chaos. This is what we call a double pendulum. Now, it's very like my leg. So imagine that's my hip, and that's my knee. So that's the bottom bit of my leg does that, and the top bit does that. Now, this is a pendulum, and it's exactly described by very, very simple laws. It's described by Newton's laws. These are things you learn at school. And for a long time, it was thought that anything that was described by Newton's laws behaved in a kind of very predictable way. And sometimes it is. There's the pendulum swinging the way we know pendulums swing. So that's behaving very predictably, and I could say exactly how long that's going to swing.
Right.
But let me show you some chaos. So again, remember, this is simply governed by laws of mechanics, Newton's laws, and all we're going to do is let it go. There's no motors in here or anything. It's just driven by gravity. Just watch it go. Now, I want you to watch that and
But it's got a certain symmetry to it, has it not?
You wait.
No.
Chaos occurs in all sorts of physical systems where we see really quite almost random-looking and unpredictable behaviour, which is simply an outworking of basic physical laws.
I'm afraid you're being upstaged by your machine.
And rightly so.
So is this the way the money markets are behaving just now?
Well, that's a very good question. The money markets are primarily driven by what's going on inside the brain. And we don't think that the brain can be easily described by mathematical formula.
I tell you what, man, after a while, looking at him, but really looking at that, we all just going to go agree, just go, yes, you're correct.
Another swing for you, just to see.
It is all random.
Oh, wow.
What this shows us is that some things which, when you look at them on the face of it, they look really, really complicated, may actually be driven by quite simple rules.
I want one of these now, man.
You want one of them?
I want one of these in my house, man. I can invite a lady over that I fancy and have her stare at it. Then I can go, I smell good, don't I?
So who's first discovered this phenomenon and how?
Well, Newton wrote down these basic laws of motion, and for about 200 or 300 years, everyone thought that because Newton written down these laws, you could predict everything. And one of the main things they studied using these laws was the solar system. And about the end of the 19th century, a guy called Poincaré, who was a French mathematician, one of the really brilliant mathematicians of his time, tried to use Newton's laws to answer a really important question, which was whether the solar system would stay stable, whether we'd carry on orbiting the sun or whether we'd go into the sun and blow up in a horrible mess.
Right.
And so he tried to predict the long-term behavior of the solar system, and he found that he couldn't. And the reason he couldn't was, again, the solar system obeys Newton's laws like this. Right. But after a while, small perturbations grow and grow and grow, and you can get these really random effects going on.
I noticed just before every time you crack into a new element of your theory, you roll that out right there. It's very clever, man.
It's fantastic. The whole of life is here.
But what about things like rooks, going to a rookery at night, and the noise, and they're going hither and thither, and they're all over the place? Are they actually acting, not chaotically, but what appears to be random? Do they have a pattern?
Well, birds flocking are a really good example of what we call a complex system. And a complex system is where you've got lots of things all interacting very closely. So rooks or starlings is another really good example.
We can show you some starlings actually, Chris, if you can talk us through what's happening.
Yeah, so each of the starlings is responding to the air currents and certain visual clues from starlings quite close to them. And the combination of all those produces these wonderful kind of coherent patterns. It's what we call emergent behaviour. So where you have lots of things all interacting, but suddenly they behave like one big organism.
Is there anything else? Give us another example of a time of chaos that wasn't random.
Well, earthquakes are probably a very good example. So we're pretty sure that there are basic laws underlying when earthquakes occur. Earthquakes are caused by one rock face slipping over another, and that's friction, and that's reasonably well explained. But unfortunately, we know that even the simple laws can produce these really complicated outcomes. And that's why it's really very hard to predict earthquakes.
So ultimately then, you cannot predict earthquakes, thus they are still random.
Well, there's a difference here between...
You might want to twip your thing around.
There's a difference between whether you can have a difficulty predicting something, it's very hard to predict that, or whether it's truly random.
Whether it's just happened by chance.
Yeah.
What practical applications does chaos theory have in our lives?
Well, it's got lots of applications. One of the great things that chaos does is it mixes things up. Right. So when you see this moving, you can see it mixing everything around. And there's lots of things in our life where we want to mix things up. And one of the things that I've worked on a lot is the design of microwave cookers.
Right.
And if you put food in a microwave cooker, a normal microwave cooker, the electrical fields can be quite regular, and that can cause hot spots and cold spots in the food, which means that it cooks not very well. And the more modern designs of microwave cookers actually try to make the electrical fields chaotic so that they kind of randomize more inside the cooker, and that gives you then much more even cooking.
All right, one last question. Is chaos theory the right name for it, do you think? From what you've said, it sounds to me like it does it a disservice.
One of the problems with the word chaos is that it can kind of mean two different things. So to a non-scientist, chaos means complete randomness. Again, going back to my dog. My dog's a spaniel and therefore behaves totally chaotically all the time. But for a scientist, chaos really means something rather different. It's this unpredictability that you get arising from scientific laws. And we can't get away from it. It's there in the universe. These mechanical systems are there in the universe doing that as we speak. Asteroids going around the sun are doing this as we speak. And one of the problems about asteroids is because we can't predict what they're going to do, one of them might hit us and we wouldn't be able to predict it.
Right.
And that's chaos.
All right. I mean, I'm wondering, I think maybe you should think of a new name. Rather than chaos, like managed mayhem theory, well, I think would be a better name for it.
Non-linear dynamics is what we call it, but it doesn't kind of have the same oomph as chaos.
No. All right then. Well, I think the time has come to reach a decision. I'll start. I think that the theory is clearly sound because you see it's observable in life that small things can lead to huge chaotic consequences. I saw it myself recently when a tiny remark about Kylie Minogue's bottom led to a massive row about what's appropriate at funerals. And it seems to me that principle is clearly observable in life. I think I understand the maths up to a point. I think you're right. I think there is nothing random about chaos. It's just that we don't fully understand chaos. That's my theory. Kirsty, what do you reckon?
I like this theory a lot, and I like it because I often observe birds at night, and I often observe birds on the wing generally, and I love the idea that they actually know what they're doing, that there's something innate that they know the way to behave, even though it looks chaotic. So I'm for it.
All right. Oh, Reg.
there's no such thing as chaos in the truest sense. It's predictable as long as we understand all there is to understand about it, which we don't, which still makes it unpredictable. So I got to shy away from this, man. I like your confidence. I like your little twirl machine, but I still got to...
All right, so that's 2 yeses and a no. Professor Chris Budd, I'm pleased to tell you that your theory that there is nothing random about chaos has been approved. And we'd like to send you away with a prize. So it's a bottle of aftershave. Because we got them in a job lot, to be honest. So if you'd like to take that with you, that's...
And this is still made of your...
Yeah.
But it's not like the other one. No 2 bottles of Andy and Reg cologne.
Thank you. Thank you, Professor Chris Budd, ladies and gentlemen.